And before we can do that, I'd like to first have another look at the topic which we know very well, at the topic which is called the matrix multiplication. So my first slide is called structure of matrix multiplication. And this is the observation which I probably made a few times already, but this I may even formalize that observation, but that's a good time to do it again. So look what I'm going to say now. If I have two matrices which are compatible in terms of the matrix multiplication, so matrix A of size m times n, and matrix B of size n times k, times k, that's right, so n rows, k columns. I'd like to look at the way we multiply these two matrices. We can multiply them. They have compatible size. The number of columns here, n, is the same as the number of rows here, n. So we can multiply them in principle, but I'd like to see this multiplication now from the structural point of view. And for that, I will introduce some new notations. Here they are. For the matrix A, I will introduce individual names to the rows of that matrix. Here we go. A1, A2, AM. Altogether we have m rows. Each of them will have this name. So individually each little a is the it's a matrix of one row and n columns. So each little symbol A1, A2, AM, they come from this class. One row, n columns, the same field of scalars. I also want to see the columns of matrix B. So matrix B will have column, and I will individually name those columns, B1, B2, Bk. Altogether we have k columns. Each column here, B1, B2, Bk, by itself, it's a matrix of size n rows, one column. This specific type of matrices we also call n-dimensional vectors. So here's my setting, and within this setting, I'd like to make the following observation about matrix multiplication. It's an observation you probably, if you've been doing multiplications for a while, if you're confident with that, that's probably the observation you have done on your own already. But I'd like to formalize it, and that's my formalization. If I compute the product of AB, which will be matrix with size m rows, k columns, rows from here, columns from here, we all know that. What I claim is this, that this matrix, if you look at this product matrix from the structural point of view, for instance, columns of this matrix will be these columns. So you see what happens? If you multiply B by A from the left-hand side, it is the same as if you multiply every column of B by A individually. That's my first observation I'd like to keep in mind for the duration of today's lecture. Each of these AB1, AB2, AB3, obviously there will be matrices of this size, right? Because B vectors individually, they were from Fn. If you multiply something from Fn by the matrix from AMN of m rows and columns, that will be matrix of size Fn. M rows, one column, or we have a shorter name for this, m-dimensional vectors. The other thing I'd like to observe is this. The same product A times B, if I want to see the structure of this product in the row sense, from the row, here's a structure in the column sense, you see? We know individual columns of the product. But if I'd like to see the row structure, then each individual row of this product will be this one. When I multiply individual rows of the left factor by B matrix, that's how the rows of the product will be. And again, each of these individual products, they will be some matrices. You see the A1 and B are compatible matrices for multiplication, right? Because we have n columns, and here we have n rows, so it's a compatible setting for taking matrix multiplication, and that's how it will be. So, shortly speaking, what I just presented is this. When you multiply the matrices, you can say this. The columns of the right-hand side factor individually multiplied by the left-hand side factor, right here. Or the rows of the left-hand side factor individually multiplied by the right-hand side factor. That's how you can shortly and formally just summarize what I have just presented. Any questions?